All right. Hope everybody's having a good day so far. Today we have two different talks, but they're both from the same group at the University of Michigan, and they both involve a similar topic. They're going to be about perfSONAR. We have three people that'll be doing the speaking duties today. I'm going to introduce Ed Colone from the University of Michigan, and he is going to give the introduction for each of the two talks. So I will hand it over to you, Ed, if you want to take it away.
I'm Ed Colone. I work for the University of Michigan and on the perfSONAR consortium. And today I have the pleasure of presenting work from two very talented interns, Abigail Fox and Nate Shepard. First, we're going to see Abigail talk about pScheduler plugin development and the S3 plugin itself. And I'll let her do the talking.
Hi, so I'm Abigail, and I'm here to talk about the S3 plugin for perfSONAR, which I developed this summer. So alongside the development of the S3 plugin, I also worked on some further development of the PDK for perfSONAR and pScheduler, which is the plugin development kit. So the plugin development kit was used for the development of this specific testing tool. And the plugin development kit itself creates a standard pScheduler core implementation on which you can on top of build your specific test tool feature set that you're looking to develop. The development of the PDK occurred alongside, the development of the plugin occurred alongside significant enhancement and extension of the existing PDK documentation. So the goal was to bring the test and tool documentation of the PDK up to the standard of the archiver documentation that I created last summer and which was released in 4.2.0. So the general usage of the PDK, it can be found in the scripts folder of pScheduler. It runs a script to create a templated version of a test, tool, or archiver, and it includes the core pScheduler elements. So basically the stuff that you need to have an empty test tool or archiver run. On top of that, you can add in all of your own functionality that you want for your specific plugin. So it's designed to make this development more accessible to anyone who wants to contribute a plugin to pScheduler. It can also streamline the development for frequent developers. It allows you to bypass the creation of the basic code infrastructure. That's all going to be generated by the script for you. So when you're getting started, all of that framework is in place and you're building on top of that, and you only need to work on the functionality that you're there to implement. So working on the documentation for this, the documentation explains the core functionality. So what is being filled in by the PDK, it explains what's there so you can familiarize yourself with it if you aren't already. And it also gives a pretty detailed explanation on how to develop and test a plugin. So some next steps for the PDK is to continue developing the documentation to streamline the development process. So as other bugs or other process things are being encountered, we like to incorporate more stuff into the documentation to help out, especially new developers. A goal is to use the PDK in future plugin development at U of M, and also to increase awareness of it for potential plugin contributors outside of U of M, people who might not have developed a plugin before, to make them aware of the existence of it. It's a tool to assist them and be able to help them create a plugin so that people who are interested in contributing a plugin are able to be more proactive about it, able to start developing it. They don't necessarily have to wait as long for someone else to pick up that project. Does anybody have any questions on the PDK before I move into S3? Okay, so I'm gonna move on and talk about the S3 plugin. So a little bit of background is that S3 storage is based on the concepts of buckets and objects. So buckets are containers that store objects. They can store unlimited objects, and the objects themselves are whatever data that you want to place there. They typically do have a size limit, but it's usually in the terabyte range, so you can fit quite a lot of data into one object. Online S3 services such as Amazon AWS use standard interfaces to make accessing this data, putting it up there and getting it back really easy. So some advantages of using S3 is that you only pay for the space that you're using. So however much data you actually have put onto the server, that's what you're going to pay for with the service. Whereas if you buy a local server, it's going to have a fixed capacity. Whether you're using all of that capacity or not, you paid the upfront cost to acquire the server. The interfaces are easy to use. And then if you're using an online service, they create multiple copies of objects and distribute them across different servers that they have. So if there is a server failure or some data loss on a server that your data was being stored in, your data will have another copy somewhere else. So you won't experience a data loss. There's also a high level of access security that's implemented by these providers, so it's not something that you need to worry about implementing your own access security. So some different use cases at U of M. Using large research data sets. Locally, these require quite a lot of dedicated server space. They can be quite large. If you store them in the cloud with S3, you're not as worried about obtaining very large amounts of server space, which can be expanding quite quickly as more data sets are being created. It can also work for any file storage. It's a really easy system to interact with, and as I said, it minimizes data loss, so it's a good protective measure. So why does S3 benchmarking matter? Why is it becoming important? So S3 is becoming more and more popular for endpoints in the cloud and on campus. So the importance of testing is definitely on the rise. The benchmarking tool can test from the source location, so the server or laptop where the data is originally being stored, and it tests it all the way to the S3 disk itself. So it's going to travel through local and remote networks. It's going to test the server hardware and processing power, and it's also going to test the reading and writing to the disk. So how long does it take for the actual data on your computer to travel through all of the networks and then end up being written or read from the disk and coming back to you? So network throughput testing isn't going to give a full picture because, as you can see, there's more components involved in the reading and writing of the large amounts of data. So for researchers, it's definitely important to understand the time it will take to actually transfer the large data set. And transferring doesn't just involve it getting there, it involves it all being written and stored so you know it's securely up there. So the S3 tool for perfSONAR is based on a tool from Wasabi, which, if you don't know, it's an Amazon AWS competitor, offers a very similar service. It's designed to measure S3 performance. So the tool itself has been adapted for use against all S3 storage servers, such as AWS, Wasabi, Minio, any server you might be using. And it benchmarks put, get, and delete operations, which are the 3 core operations at the heart of S3. So put does what it sounds like. It takes the objects and it puts them on the server. Get also does what it sounds like. It gets the objects from the server and returns them to you. And delete removes the objects from the server. So the capabilities of this tool and the configurability, there's the ability to specify the duration of the put. So this is the core way to control the duration of the test. So the duration of put will basically put as many objects as possible during this given duration. So with the duration of, for example, 30 seconds, it's going to run and try and put as many possible objects of a size that you specify onto the server in 30 seconds. The get and delete operations of the benchmarking tool depend on the number of puts, because get and delete tend to be much faster than putting because it's not necessarily writing all of this data to the server. So if the duration specified for the put is 30 seconds, the test might be 40 seconds long, with the other 10 seconds belonging to get and delete. Get being a little bit slower than delete, delete is really fast. The tool also offers the ability to run consecutive loops, so you can repeat the test the specified number of times and you can get some averages and individual loop statistics. You can also specify the object size, so the default is 1 megabyte, but you can also use this to simulate more realistic large data transfers, such as 1 gigabyte objects. So if your research data set, the objects themselves are really large, you're able to simulate that as well. You can also specify which bucket you want to test against. So you can create a temporary bucket for testing. If you provide a bucket name that doesn't already exist when running the test, it's going to create it for you and then use that bucket. Or if you're wondering how a specific bucket is performing, you already have some data in that bucket, you want to see how it's doing, you can test against a specific bucket in the service. And it's going to go access your individual bucket that already exists and put and get objects from that spot. And as I mentioned before, it can be run against any S3 server. So now I'm going to do a demo. Does anyone have any questions before I do the demo? Okay. So I'm going to open up my terminal and share that screen. Okay, I'll make it a little bit bigger. Okay, so an example command that you can run this. Can everyone see this okay?
Abigail, if you could make the text a little bit larger, that would help all of us with old eyes.
Of course. All right.
That's great.
Just clear it. Oh, there we go, to get back to the top. Cool. So here's an example command that you could use for running this. So let me move the little Zoom bar if I can. Oh, okay. So, and here's an example command that you could use. So obviously you're specifying the task, it's S3 throughput. You do need to provide your access key. So your access key is gonna be specific to your server, as is your secret key. So that's the information that you need to specify that the data is being put on your specific designation of the S3. You also need to specify the URL and the access method. So play.min.io is an example, kind of like a dummy server provided by Minio. Anybody can use it. You can put data up there. People use it to run tests, basically. The bucket that's being specified is pscheduler test. It's just a bucket that's going to be created, sort of a generic test bucket. It's not a specific bucket that's already there. You can also specify the duration. The default is 30 seconds, so that's what I'm going to be using, but you could specify any number of seconds that you like. As I mentioned, the default for size is 1 megabyte, which is what I'm going to be using, but you can vary that. I'm using these presets because I'm doing this from my house and my Wi-Fi is not very fast. So in order to get a meaningful number of objects. However, I have run this on campus Wi-Fi, which is quite a bit faster. And it was able to do about 200 objects in 10 seconds, whereas I'm not able to get nearly that many. So obviously the performance does depend on your network as well as everything else. Does anyone have any questions for me while the demo is running?
I guess I have a question.
Yeah, of course.
How can you enable an existing pscheduler to incorporate this test? And when will it be, and this, when will it be distributed with perfSONAR, if ever?
So this is going to be distributed in 4.3.0. So after that, you'll be able to run it with any of your pscheduler installations.
So we did have a question come in on the chat room that I can ask before you go into the explanation of what's going on there. James Deaton wanted to know, or comments, I was told that the PDK would make the development of S3 tests possible, and to see it implemented and available is great. So thanks for the comment, James.
Yeah, the PDK definitely made it a lot easier and a lot faster to develop this. And it was really nice to, as I was developing this, be able to improve the PDK as well. So if someone was doing something similar again, it would be really fast. But here we have the results from the demo. So as I said, it took about 40 seconds to run. So the limiting part is the 30 seconds for the put operations. The rest was dedicated to get and delete. So I just ran one loop. It spent 30.8 seconds putting objects. It was able to put 13 objects in that time. You can get an average speed. The get and delete number of objects is going to be the same as the put, because it's just going to be accessing the objects that the process itself put up there. And the objects themselves are just filled with random data. So it's not anything in specific. A bunch of random data is generated, a random configuration of bytes to occupy the amount of size of an object. The average put time, average get time, and average delete time are offered. Since I just did one loop, it's average across the total time per loop and the number of objects in the loop. If there were multiple loops, it would be averaged across all of them as well. So you can see that a put is definitely the longest operation. It takes about 2 seconds on my Wi-Fi to put an object up there, whereas it takes less than a second to get it back and very, very little time to delete it. Does anyone have any questions on the demo?
No questions yet in the chat room, but I'll encourage everybody, if you do have anything, please type it in.
And I'll head back to the slides. I have a few. Oh, question.
James has a follow-up. Do you have an instance in place that shows results over time?
No, not yet. So the only overtime that this will do is if you run consecutive loops, those will be recorded over time. In order to get like true overtime statistics, you'd probably need to schedule this with pScheduler and compare the results from one iteration ran with pScheduler to the next by storing it in an archiver or something similar. But that's definitely not off the table for future improvements. Okay, I'm gonna head back to the slides. Okay. So yes, there are some next steps that we envision for S3. Expanding support for multi-threaded testing against an S3 endpoint. This is an available capability. If it's something that would be important to have implemented, it's definitely there and could definitely appear in the future. There's also the possibility of optimizing test duration and object size suggestions for different use cases. So right now the defaults are just 30 seconds and 1 megabyte. You can obviously control and customize everything as much as you want, but it might be nice to offer some provided defaults so that, for example, if you're a researcher who deals with large objects, there would be an option for you that you just get to select as a preset, and you don't necessarily have to fiddle with what you would expect your parameters to be. So just offering some different suggestions for what makes sense. Does anyone have any questions?
Yep, we had one more come in. Doug wants to know, is there any way to verify where you are testing to? For instance, if you get drastically different test results on different days, would you be able to tell if you were actually testing to a different data center?
That's an interesting question. I'm not sure if that's available right now based on the tool. I can definitely look into it. If it's something that's available in the underlying tool, then it's something that's definitely capable for implementing. If it's not, it would be a little bit more difficult just because the tool that underlies this is currently being maintained by Wasabi. So if it was something that wasn't currently available, it might be a little more difficult to add because it would require us to essentially branch off our own version of that and maintain it. But I will definitely look into that.
I would also like to add, and Abigail taught me this, is that if you send this to a random bucket in, you know, Amazon's S3 cluster, then it might have different performance than what your live data is. But if you send it to the same bucket that your live data lives in, it should get the same performance that people see with live data. And I'm going to let Abigail expound upon that and correct me if I'm wrong.
No, yeah, that's totally right. It's because when you use a random bucket, it could end up on any of the different servers or data centers. It's just going to add it. Basically, it tries to optimize it. So it treats it as though you were actually trying to create a bucket and actually trying to add data. When you're actually creating a bucket and adding data, Amazon, Wasabi, whatever, it wants to give you what's going to have the best performance right now. When you're testing to an existing bucket, that existing bucket is stored on a limited number of servers, a limited number of data centers, and it's going to need to access one of those instances. So it does try to optimize that in general, Amazon does, but it's going to be the same performance as if you were writing objects, your quote unquote real objects and real data sets to the same bucket. The server itself doesn't see any difference between the traffic generated by the test and real traffic. So if you were creating like a junk bucket in like your Amazon interface or whatever, it would treat that the same as a junk bucket, but the advantage is that the real bucket is the real bucket, it exists, it's going to be treated the same.
Okay, no additional questions right now.
I have one comment, and that's that I really appreciated everybody's input, and we're going to put on our next steps that we're going to make sure that data archiving and data visualization are also taken care of. So I appreciate the comments.
Okay, if anybody else does have questions, please type them in. But if otherwise, we may want to switch over to Nate's presentation.
Indeed. And now I'd like for Nate Shepard to show us his presentation on embedded systems.
All right, hey everybody. Today we're going to be talking about the embedded systems project, and I will share my screen so you guys can see my slides. All right, we're going to try and keep this short and sweet. So essentially the question that my project was trying to answer is given here. We're trying to see the interaction of clients trying to connect to deployed hardware, as well as the effect that those clients have on the network and the performance of hardware that's deployed. Typically in this situation, you would have to have your device configured and installed somewhere on your campus or university, for example, and then wait for high performance times where you have a lot of people in the building, or see how it performs when there's nobody in the building, for example. And some of the drawbacks of that approach is that we have to wait time in order to get the information metrics about how our devices are performing. But another approach would be to simulate the realistic environment of clients connecting to your server in a contained and controlled manner, so that we might be able to get information about how the device would actually perform in the real world once we actually deploy it at larger scale. And this is in fact what we did, and this is an example of the test harness configuration, which we used to test 2 different routers given by different vendors. You can think of it as a secure way of accessing the lab as this big blue rectangle, which we reference as the Bastion host, and gives us a way to securely access the lab where we do all of the testing. And then connected to the Bastion host is 2 routers, Cisco and Arista, and connected to those routers are different servers, which are basically either simulating traffic on the network or testing the network. Additionally, inside each of the routers is another perfSONAR container as a virtual machine, which is able to do testing on the network from within the router. The way that we're able to simulate the traffic in order to get an idea of how our hardware might be performing under realistic conditions is by using this open source traffic generator called T-Rex. Essentially, T-Rex is a scalable way of generating specified flows of traffic data onto our network to specific devices. You're able to specify, do you want to have certain types of internet browsing traffic, SSH traffic, video calls, etc. And you also have the option to scale the amount of information being sent by each of the clients over time as well. The output of T-Rex is a long list of metrics, like several pages for each test. And part of the difficulty with that is that there's almost too much information about the network that T-Rex is giving you. But the reason why we chose this tool specifically is because it's easy to use. It's just command line interface type starting tasks, as well as you simply download it and install it and you're ready to go. It also has a way to automatically detect which interfaces are connected to each of the devices, so that you can specify where and how you're actually sending the data across the network to each device specifically. And the way that I was able to simplify the process of T-Rex actually sending this data across the network was by writing a Python-based automation tool, which is able to execute the tests, determine what the tests are exactly, as well as get the information back from each of the devices without having to individually SSH into all of them, and then backing it up, doing data analysis, and essentially simplifying the whole process of simulating traffic on any switch. It's also a very secure method where all you have to be is a agent on your local computer within a recognized virtual machine VPN, so that you can SSH through dual authentication to the Bastion host. And the Bastion host has all the testing details in order to execute and get the files from all the specific devices and do the data analysis locally. You can also check out this project on my GitHub. It's my username, just my name, and then this one is called Infrastructure Testing as a project. These next few slides are a way of describing the historical progress of this test lab configuration, as well as some of the limitations that we've encountered and how we've overcome them. This image on the right-hand side is an example of what the internals of a router would look like, wherein we have the data plane, which can be thought of as a finite state machine, which receives forwarding requests for the open internet and basically handles all that based on the rules that it has. These rules are negotiated by the control plane, which sends the information about how to route traffic over the bus. And the control plane is kind of thought of as a mini computer within the router, which can determine these rules based on what kind of information the data plane is handling. And inside the control plane, we have the perfSONAR testing tool deployed as well, so that we can understand things about the network that we wouldn't necessarily have access to from outside the network. But part of the problem with the situation is that we have to communicate with pScheduler over the bus, which is the way that the control plane communicates with the data plane, and it's only got about a gigabyte per second performance for throughput. So some of the ways around this that we've thought of is using the management port in order to have the device self-loop and execute data requests over the data ports. However, this has an interference with the network administration tasks that might be present, and we would not like to have the additional complexity of an extra cable connected to the device. Another approach to this problem is to have the information from the perfSONAR node inside the control plane send data over the bus and then back through the data ports in order to have this maximized throughput performance on the data port without being limited by the bus. However, it requires an external cable, and we wouldn't like to see this self-loop contained within a single device. But part of the advantage of this specifically is that we can use the pre-switch virtual interface SVI. And the SVI is even simplified in this example, where we're able to not have an extra cable. Essentially, the control plane with pScheduler on it is able to communicate to the data ports without having an external cable. So internally, it's determining which ports are not being used in order to use those. And in this way, we don't have an extra cable, and we aren't interacting with anyone that has to use the data ports, so that the data being sent is maximized and we aren't limited by the limitations of the bus.
So I'm going to stop you there, Nate, because we had a question come in. Hans wants to know, have you worked with any switch or router vendors that have an x86-based system next to their control plane?
I'll take that one. I'm going to say that we've had the pleasure so far in our lab of testing Cisco, Arista, and Juniper gear. We have not had a chance to test anything by Mellanox or other vendors. We are to understand that some of them do have higher throughput performance. We just haven't had the ability to get them in our lab yet.
Okay, thank you.
Okay, if there's no other questions, I can move on. So essentially what's drawing this all together is we want to understand the difference between a embedded solution, which is what we were just talking about, pScheduler installed within the control plane on the router, to having a separate node, which is thought of as a separate server which has perfSONAR installed on it, which tests the network that the router is a part of from a separate network. And we're addressing the idea that we won't be able to have a misidentification of the network performance. And in this case, we have a graph which shows the throughput of a Dell with T-Rex installed on it, which kind of scales up the amount of clients per gigabyte so that we have a high amount of throughput traffic generated. And it's compared to the CPU utilization on the Dell, which is generating the traffic. And it's being sent in two cases for the two lines to two different routers. One is the Arista router, and the other is the Cisco 9300. And the Arista is the 720 XP, I believe. And we notice that at a certain degree of throughput, which is about its maximum at 8 gigabits per second, we notice a difference of 12% in the CPU utilization given this controlled testing environment. And the exact reasons why this difference is occurring at this case, as well as at the more beginning of the test where we see some switching between who has the maximum CPU utilization versus the minimum, is an open question. And there's still research being done to investigate exactly the causes for this difference. And here's another example of the advantage of using these T-Rex flows in order to generate traffic, is that you can specify, do we want simple traffic or complex traffic? And which device we want to send it on, and what does that data look like? And using my automation tool, we're able to generate these graphs very quickly and easily. And you can see that there is some difference in the handling of these two different traffic flows. And we can describe the simple traffic as being simply HTTP, GET, requests, posts, as well as complex traffic being a larger array of internet protocols such as FTP, SFTP, HTTPS, etc., maybe even video calls. And we can see that the Cisco device was on initialization having a more difficult time handling the complex traffic compared to the Arista. And especially towards the ends of the test, we notice a difference in how the CPU utilization is relating to the client throughput on the device. And yet again, another open question, and there could be a lot of variables interacting in this situation. So the next principle that we're trying to address here is that our performance of a specific node testing the network is what we would expect it to be given the environment that it's in. And this graph here on the right, you can be thought of as a way of showing how often we see the expected throughput versus what the actual throughput was on a isolated environment. So this is literally just the virtual machine within a router. While the router is not doing anything, pScheduler tests throughput from the device to the device. And this test was run several hundred times for about 10 seconds each. And the way that you can read this graph is, for example, on the right-hand side of it, we have a 2.05 throughput, which was the maximum throughput measured. And since the y-axis is about 0.1, this is the probability of throughput. So we can say that for every 100 tests, we would expect 10 of them to have a throughput of 2.05. So we had expected that the throughput would be at what Arista said was the maximum at about 2 gigabits per second. But given these test data, we were seeing in a realistic environment that the expected throughput was more closely 1.6 gigabits per second. We would also like to include other manufacturers for this graph and have other graphs generated. But right now we only have the Arista, and we would like to include Cisco and Juniper within as well. Here's another graph to show an extension of the previous slide, where the previous slide would be just the x-axis being at 0. And you could see that there was some variation, but we would just put the maximum throughput for the entire duration of this test, which was scaling up clients, testing or having traffic routed through the Arista router while the router is doing pScheduler traffic testing using throughput. And in this way, we were able to notice some experimental difference between not having any traffic on the device versus scaling up the traffic, wherein the amount of pScheduler throughput that was being able to put through the network was decreased by at most 20%. And the reasons for this is an open question, and there could be a lot of factors at play, specifically the router's routing of traffic, the Dell's CPU utilization, optimization, as well as other factors in the network that are still an open question.
So we did have another question come in. If you want to stop for a second, Nate.
Yeah.
Ken Miller wanted to know, have you used T-Rex to do any RFC 2544 or Y.1564 tests on network gear? Or have you compared the T-Rex expected traffic rates versus other measurements like SNMP or NetFlow or SFlow?
I'm gonna try to help take this one too. So T-Rex out of the box doesn't, I don't think that it does RFC 2544 to spec. Instead, they have different traffic profiles that come sort of pre-canned for you for different observed real-world situations. You're also able to use T-Rex to, and Nate can correct me if I'm wrong, to record traffic at different points on your network and then sort of replay that.
Yeah.
The other thing that it comes with is it comes with a few benchmarks. Like there is one called SFR that was developed in France for different network testing exercises that they were doing. It includes that one. And I don't know what Y.1564 is. I'm also going to say that we have not compared it versus SNMP or NetFlow, IPFix, or SFlow. So,
yeah, the T-Rex program is an open source tool. So the ways that they are generating the traffic and the templates they're using are also manually editable. So if, for example, there's some protocol which is not supported by T-Rex, and in this case, I'm not sure exactly if the tests that you mentioned are included in the main test words testing suite, but there's the ability to include those if you feel like that's a required situation where you're going to be putting this generated traffic onto your device under test. So in this case, I don't think we have actually encompassed the test that you're referencing, but it's definitely a capability of T-Rex if it's something you're interested in.
Okay. And we had one other question here. What are the possibilities for open hardware switches running an open NOS?
the sky's the limit. I mean, I don't really know, but if there was some, right now we're testing specific vendor products. If there was some sort of standard or particular recipe for an open hardware switch, and we could test it in the lab, we would be happy to. I also see that Eric Boyd has his hand raised.
Yeah, let me see if I can unmute you, Eric. Hopefully you're in a semi-quiet area.
Yep, I am.
Okay, there you go, Eric.
Nate, if you could go back a couple slides to the one where you're showing the flow through the router.
Yep. Was it
Keep going. Keep
this
going.
one?
No, keep going. The architecture, that one. So in both of these that Nate presented, you have to go through the bus, or essentially you have perfSONAR running on the control plane, and you're limited in some way by how you're getting to the data plane. One thought that I had that I'm not sure you can do with like Arista or Cisco, although we have mentioned it to them, but perhaps you could do with a more open plane. There's really no reason to actually send all the data across the bus. If you could simply say, look, I want a packet filled with random bits sent from the data plane, and all you had to do was signal the creation of it, but not actually send the whole packet, I think this would work a whole lot better. So it's, to me, the interesting thing would be is there an existing architecture out there where we could show that, where you're not actually sending the test traffic, but you're sort of spontaneously generating it out of the data plane. That was my only comment.
Yeah, I definitely think that this approach would be possible because, like right now, we're having the control plane node sending the pscheduler data and also storing it on itself. But it might be possible to have the test itself be configured on a central management server that's separate from the router itself. And then we'd be able to specify that the data is being sent and returned to the data plane in this router, but then storing all of those data metrics on a separate device instead of having that data being sent back through the bus in order to communicate with pscheduler again. So I think that moving forward, that's an option that we can explore further.
Okay, it doesn't look like there's any other questions, so you can continue.
Alrighty. So that kind of draws back to the next steps where we have different vendors which have interest in sending us their devices to further test with. Specifically the Arista, we would like to refine the test that we've already done on the router and to the router from T-Rex in order to get more specific metrics and investigate these questions, such as the difference between the CPU utilization, as well as the interaction between pscheduler and network traffic. And we would need to get another loaner from them again in order to continue with this investigation. For Cisco, we already have the test designs and we've already begun some of the testing, but Cisco would like us to have the USB stick in order to have publishable results about their devices. For the
I'd like to expound upon that just a tiny bit. We had previous embedded systems presentations at TechX a few years ago, and we did publish Cisco results then. Since then, Cisco has changed their configuration to use a specialized Cisco USB storage device, and they're allowing us to run tests still in the lab with the old configuration, but they don't want us to be able to publish any of them until we are able to run with the sanctioned Cisco storage and Cisco primary configuration that they're going to basically release as a vendor product. So we're still waiting on them to get us that storage device. But when they do, we're going to reconfigure to their new spec, and then we're going to retest. Eric's got his hand up again.
All right, hold on, Eric. You are unmuted.
Yeah, so what I would say is this kind of goes towards the total cost. So in my mind is running the campus network at Michigan. I'm looking at the total cost to deploy perfSONAR across campus and be able to afford to maintain it. And obviously we could buy network devices to put next to our routers as a way to be sort of a proxy for the routers themselves. But if there was a way to embed them on the devices, that would probably lower my hardware costs and theoretically would also lower my support costs as well, because it would be a software product embedded in the router, not necessarily having to send somebody out every time one of the little devices failed. Of course, depending on how each vendor does their support for running software in containers on their device, that could significantly change that cost calculation. So if the cost of a USB stick, for instance, ends up being significant, then you might have to weigh that again. Is it really worth embedding it on the switch or itself?
Yeah, definitely. And exactly the motivations behind why you would choose one of these vendors over the other is the question that we're trying to investigate. For each of the devices that we've tested with already, we had a virtual machine with perfSONAR installed on it and did all this testing in order to try to understand, is the perfSONAR node performing better within the router than it would compared to one outside the router? And what's the effect on the client traffic in that situation? We're also trying to get a sense of how easy it is to deploy pscheduler within the routers for each of the different vendors. And once we've done that for all of them, we've only done them for Cisco and Arista, we'd be able to tell you, like, it's this difficult to install it and this difficult to keep up with it. And its effect on the network is this specifically, and you're going to expect this difference in client performance.
So one thing I would like to mention that Nate has not mentioned yet, and may have even started taking for granted, is that a large portion of Nate's time has been spent actually installing and configuring these packages on different platforms. And right now, I would very comfortably say that for all of the platforms, it's fairly non-trivial to get this working. Just, I mean, even in a test lab, it's non-trivial. So kudos to Nate for hanging in there and actually doing a lot of this configuration and testing, because it's not been easy.
Yeah, it's definitely difficult to get started. I think that the major difficulty here for installing is getting it to install the first time and actually having it be stable. But once we negotiate with the network team and we have a stable setup, I think that deploying another software and hardware, which is the exact same, would be non-trivial. But if any changes or updates to the software or the software version, or it's a different device, yeah, like you're saying, it's very difficult to get it up and running.
And along those lines, there was a comment that came in that if you do have any tips and tricks for your experience, putting them on your GitHub page or in one of the perfSONAR docs probably would be really helpful.
Okay, yeah, I'll take note of that. Right now I just have like the test design, the test data on my GitHub, but including specifically what steps I was taking have already been included in my own private database, but I can include those publicly as well.
And then one other question, and maybe you'll get to this since we didn't quite get to the Juniper piece. Are you looking at the Juniper NFX 2050 at all? Or I'm sorry, yeah, 250 at all? And any testing with disaggregated Junos OS?
We have not tested with disaggregated Junos OS. We are working. So I'm gonna steal Nate's thunder here on his last point. We are working with Juniper. They're currently sending us a QFX to our lab, and we're going to collaborate them with building and installing a perfSONAR container. I imagine that's going to be a very non-trivial effort, because they have certain container demands and build practices, and I think it's going to fall upon us to kind of follow those to build the perfSONAR container. So it's going to be a non-trivial effort to get perfSONAR running on Juniper hardware. I don't know much about the NFX 250, I must admit.
I would add something here. So for folks who saw the presentation a couple of years ago, one other thing, and correct me if I get this wrong, but I think that, you know, the support for containers on these devices is still very much in flux. And sometimes we're sort of retreading existing ground because the vendors have changed how they want us to do things. So I think we're a fair distance away from, you know, a standard way of doing this and being easy to do. You get the sense sometimes that Nate was their first customer.
Indeed. I'll echo that, and I'll say that it's so diverse across the manufacturers that we have tested with that each one of them even has a different container scheme. It's not just like, oh, just use a Docker container and you're done. There's you know, differences across the board.
Okay, we don't have any more questions at this point.
Okay, there's just one more slide just talking about the contributors and contributions to this project. You know, obviously Eric Boyd is kind of like the head of everything, and then we have Edward Colone, who was very much supervising my work over this. Phil Camp was able to help us out in the network lab, actually installing the hardware part of things so that I could configure the software side of things. This slide presentation wasn't entirely composed by myself, and some of it was neatened up by our graphic design partner, Katarina Thomas, as well as some groundwork that was laid for the installation of Cisco software and hardware by Ryan, our previous intern, and part of the project as well. And additional thanks to the Cisco, Riska, and Juniper team, who have been very helpful in terms of helping us when we have hit the wall and are having trouble moving forward with the projects, and giving us help with some of the errors that we are reaching, as well as letting us test with their devices temporarily. And my contributions to the project have mainly been the automated network performing testing suite, as well as the comparison of realistic traffic interactions, both on the network and hardware, and also independently, dependently, so that we have network testing performance of the router independent of any other traffic, as well as traffic and the router's performance being interplayed and graphed using this automatic testing suite. And that's my presentation. Any further questions?
All right, well, thank you so much, Nate and Ed and Abigail, for all that. There's just been some other chat in the chat room, mostly about the configuration tips and tricks. So hopefully you'll be able to share out some of that stuff. Also, Cindy, Cindy is still on. Cindy, send Ed an email about your offer of testing the Mellanox equipment. All right, if anybody has any other questions for the chat, for either presenter, please type them in now. Otherwise, I think I'll turn it over to Ed, because Ed, you have a couple of other talks next week if you want to tease out the topics at all.
Sure thing. This kind of concludes the internships of Abigail and Nate with plugin development and embedded systems research. Next week, we're going to showcase two other internship projects. One of them is a collaboration between us and Jayant to deploy and automate the Wi-Fi monitoring system that they presented at TechX 2019. And the other one is a brand new piece of software being developed at the University of Michigan called PSID, which is an active Wi-Fi monitor that examines network performance at the BSSID level and uses the ELK stack for data gathering and visualization.
All right. And doesn't look like any more questions. So thank you all three for your time today. And for those that are listening, we'll be back next week on those topics. So hope everybody has a good weekend, and we'll talk to everybody soon.
Thank you all for coming.